Right now you're looking at a galaxy, a swirling island of light containing hundreds of billions of stars stretching across unimaginable distances. But what if it's not just a natural wonder? What if every glowing cluster, every spiral arm, every radiant core was built? Imagine galaxies not as cosmic accidents, but as vast alien megastructures, engines of energy, consciousness, and purpose, constructed on a scale beyond comprehension. Tonight, we journey to the edge of known science and deep into the frontier of possibility. Through Dyson swarms the size of solar systems, civilizations that sculpt light itself, and the haunting question, what if the universe is their design? If you're ready to rethink reality itself, let the journey begin.
What if the galaxies we see glittering in the darkness aren't just clusters of stars, but colossal, artificial structures built by civilizations so old, so powerful, that their technology spans the cosmos itself? Look up on a clear night, far from the glow of cities, and you might catch a glimpse of the Milky Way stretching across the sky like a river of light. Billions of stars, each one a sun, each one burning with nuclear fire. We've been taught to see galaxies as natural formations, cosmic accidents born from gravity and gas clouds collapsing over billions of years. But what if that story, comfortable as it is incomplete? What if those spiraling arms of light, those elliptical clouds of ancient suns, are not random at all, but designed? What if they are machines? The question sounds impossible at first. Galaxies are so vast that our minds struggle to hold them. The Milky Way alone contains somewhere between 200 and 400 billion stars spread across a disk 100,000 light-years wide. To imagine that something so enormous could be artificial feels like madness. And yet the universe has always been stranger than we expected. Every time we've looked deeper, we've found patterns we didn't anticipate, structures we couldn't explain, mysteries that refuse to resolve themselves into simple answers. So tonight, as the darkness settles and the stars begin to appear, let's ask the question that astronomers whisper about in private, that science fiction writers have danced around for decades, that ancient myths might have been trying to tell us all along. What if galaxies aren't born, but built? To understand why this question matters, we need to start with what galaxies actually are, and why they've captivated human imagination since the first person looked up and wondered what those faint smudges of light could be. For most of human history, we didn't know galaxies existed. The Milky Way was visible, of course, that pale band of light crossing the night sky, but we thought it was just a cloud, a river of milk spilled by the gods, a road for spirits to travel. The ancient Greeks called it Galaxias Kyklos, the Milky Circle. The Romans saw it as the path to heaven. In Norse mythology, it was the bridge between worlds. Every culture had a story, but none of them knew the truth. That we were looking at our own galaxy from the inside, seeing the combined light of billions of stars too distant to resolve individually. It wasn't until the early 20th century that we discovered the universe was far larger than anyone had imagined. Edwin Hubble, using the most powerful telescope of his time, proved that the faint spiral nebulae scattered across the sky weren't clouds of gas within our own galaxy. They were entire galaxies themselves, island universes separated from us by millions of light-years of empty space. The universe, in an instant, became unimaginably vast. Today, we know there are at least 2 trillion galaxies in the observable universe, 2 trillion separate collections of stars, each one containing billions or even trillions of suns. They come in different shapes, spirals like the Milky Way, with elegant arms curving outward from a bright central bulge, ellipticals, which look like smooth, featureless clouds of ancient stars, irregulars, which have no clear structure at all, as if they've been torn apart by gravitational forces. They cluster together in groups and superclusters, connected by invisible threads of dark matter, forming a cosmic web that stretches across the entire universe. The standard story of how galaxies form goes like this. In the early universe, just after the Big Bang, matter wasn't evenly distributed. There were tiny fluctuations in density, regions where gas and dark matter were slightly more concentrated than elsewhere. Gravity amplified these differences. The denser regions pulled in more matter, which made them denser still, which pulled in even more matter. Over hundreds of millions of years, these regions collapsed into the first galaxies, small, irregular collections of stars that would eventually merge and grow into the massive structures we see today. It's a beautiful story, and the mathematics supports it. Computer simulations can recreate the cosmic web, showing how galaxies should form and evolve over billions of years. The predictions match observations remarkably well, and yet there are anomalies. There are always anomalies. Some galaxies rotate too fast. According to the laws of physics, the outer edges of spiral galaxies should be moving more slowly than the inner regions, just as the outer planets in our solar system orbit more slowly than the inner ones. But when astronomers measured the rotation speeds of galaxies, they found something strange. The outer edges were moving just as fast as the inner regions, sometimes even faster. The galaxies should be tearing themselves apart, flinging stars into the void, but they don't. Something is holding them together, something we can't see. We call it dark matter, and we've built elaborate theories to explain it. Invisible particles that don't interact with light, forming halos around galaxies, providing the extra gravity needed to keep everything in place. It's a compelling explanation, and most scientists accept it. But dark matter has never been directly detected. We infer its existence from its gravitational effects, but we've never captured a single particle, never seen it in a laboratory. It's a placeholder, a name for something we don't understand. What if the anomaly isn't caused by invisible matter at all? What if the galaxies are rotating the way they do because they were designed that way? To explore this possibility, we need to talk about the Kardashev scale, a framework for measuring the technological advancement of civilizations based on how much energy they can harness. The scale was proposed in 1964 by Soviet astronomer Nikolai Kardashev, who was thinking about how we might detect advanced alien civilizations. He realized that as a civilization becomes more technologically sophisticated, its energy consumption increases. A primitive civilization uses the energy available on its home planet: wood, coal, oil, eventually nuclear power. But what comes next? What happens when a civilization exhausts the resources of its planet and needs more? Kardashev proposed 3 types of civilizations. A type civilization can harness all the energy available on its planet, every ray of sunlight, every gust of wind, every tidal wave, every volcanic eruption. Humanity isn't quite there yet. We're somewhere around 0.7 on the scale, still burning fossil fuels, still wasting most of the energy that reaches us. A Type 2 civilization can harness all the energy of its star. This is where things start to get interesting. To capture the total output of a sun, you would need to build something enormous, a structure that surrounds the star, collecting every photon it emits. This concept is called a Dyson sphere, named after physicist Freeman Dyson, who proposed it in 1960. A Dyson sphere wouldn't be a solid shell. That would be structurally impossible, but rather a swarm of solar collectors orbiting the star, forming a cloud that intercepts most of its light. From the outside, a star surrounded by a Dyson sphere would appear dim or even invisible in visible light, but it would glow brightly in infrared as the collectors radiated waste heat. And then there's Type Thesis. A Type 3 civilization can harness the energy of an entire galaxy, every star, every supernova, every black hole. To do this, they would need to build structures on a galactic scale, coordinating the energy output of billions of stars. They would need to think in terms of light years and millions of years. They would need to be so advanced, so patient, so fundamentally different from us that we might not even recognize them as alive. But if such a civilization existed, what would it look like? What would it build? One possibility is that it would build the galaxy itself. Think about it. If you're a Type 3 civilization, you don't just harvest energy from existing stars, you arrange them. You move them into optimal positions, creating patterns that maximize efficiency. You might build artificial stars, or modify natural ones to burn longer and more steadily. You might construct vast networks of energy collectors, linking stars together into a single, unified system. You might even shape the galaxy's structure, sculpting its spiral arms or adjusting its rotation to serve some purpose we can't fathom. From our perspective, looking at such a galaxy through our telescopes, we would see what appears to be a natural formation. We would measure its light, calculate its mass, observe its rotation, and conclude that it formed through ordinary gravitational processes. We wouldn't suspect that every star was placed deliberately, that every spiral arm was engineered, that the entire structure was a machine built by minds that existed long before our sun was born. This is the terrifying beauty of the idea. A sufficiently advanced civilization wouldn't need to announce itself. Its technology would be indistinguishable from nature. Its megastructures would look like galaxies. Its power plants would look like stars. And we, looking out at the universe with our primitive instruments, would see only what we expected to see. A cosmos shaped by physics and chance, not by intelligence and design. But what if we're wrong? What if the universe is full of these structures, and we've been staring at them all along without realizing what they are? The idea that galaxies could be artificial connects to something deeper in human consciousness. The ancient intuition that the heavens are not random, but ordered. That the cosmos is not chaos, but architecture. Every culture that has looked up at the night sky has seen patterns. The Greeks saw heroes and monsters written in the stars. The Babylonians mapped the movements of planets and predicted eclipses. The Maya built pyramids aligned with celestial events, tracking the cycles of Venus with astonishing precision. The Egyptians oriented the Great Pyramid to true north with an accuracy that modern engineers struggle to explain. Across the world, separated by oceans and millennia, humans have looked at the sky and sensed that it was designed, that someone or something had arranged it with purpose. In many mythologies, the heavens are literally the home of the gods, the place where divine beings live and work. The stars are their cities, the planets their chariots, the Milky Way their road. The universe is not a dead expanse of matter, but a living realm populated by intelligences far greater than our own. And while we've learned to dismiss these stories as primitive superstition, as metaphors for natural phenomena that ancient people didn't understand, what if they were trying to tell us something true? What if they looked at the sky and saw what we're only now beginning to suspect, that the cosmos is not natural but made? Consider the concept of the celestial spheres, which dominated Western astronomy for nearly 2,000 years. Ancient and medieval astronomers believed that the planets and stars were embedded in crystalline spheres that rotated around the Earth, producing a divine harmony as they moved. The idea seems absurd to us now, but it was based on careful observation. The planets do move in regular patterns. The stars do appear to rotate in perfect circles. The universe does seem to follow mathematical laws. The ancients looked at this order and concluded that it must be the work of a cosmic architect, a divine intelligence that had built the heavens like a vast machine. When Copernicus and Galileo overturned this model, replacing it with a sun-centered system governed by gravity and inertia, we thought we had banished the architect from the cosmos. The universe, we learned, runs on its own, following laws that need no designer. But what if we were too hasty? What if the order we see in the universe, the mathematical precision of planetary orbits, the elegant structure of galaxies, the fine-tuned constants that allow life to exist, what if all of that is evidence not of natural law, but of engineering? There's a concept in theology called the argument from design, which says that the complexity and order of the universe point to the existence of a creator. For centuries, this argument was used to prove the existence of God. But what if the creator isn't divine in the traditional sense? What if the architect of the cosmos is simply an older civilization, one that reached Type 3 status billions of years ago and reshaped the universe to suit its needs? This idea appears in science fiction, of course. Arthur C. Clarke's novel 2001, A Space Odyssey, features alien monoliths that guide the evolution of intelligent life. Isaac Asimov's Foundation series imagines a galactic empire that spans millions of worlds. Greg Egan's Diaspora explores civilizations that exist as pure information, reshaping matter and energy on cosmic scales. But these stories are usually set in the distant future, imagining what humanity might become. What if the future already happened? What if the universe we inhabit is the product of that future, and we're just late arrivals, living in a cosmos that was built long before we existed? The ancient myths might have been closer to the truth than we realized. When they spoke of gods in the heavens, they might have been describing Type 3 civilizations. When they said the stars were divine, they might have meant that the stars were artificial. When they claimed the universe was created, they might not have been talking about magic, but about engineering on a scale we're only now beginning to imagine. So how would we know? If galaxies are megastructures, what evidence would we expect to find? The challenge is that a sufficiently advanced civilization would be very good at hiding. If they've been around for billions of years, they've had plenty of time to perfect their technology, to eliminate waste, to make their structures blend seamlessly with natural phenomena, but no technology is perfect. There should be anomalies, small irregularities that don't quite fit the standard models, patterns that seem too precise to be random, energy signatures that can't be explained by known physics, and when we look closely, we find them. Start with galactic rotation curves, which we mentioned earlier. The fact that galaxies rotate faster than they should has been known since the 1970s, and dark matter is the standard explanation. But there are other possibilities. Some physicists have proposed modified theories of gravity, MOAND, or modified Newtonian dynamics, which suggest that gravity behaves differently on galactic scales than it does in our solar system. These theories can explain the rotation curves without invoking invisible matter. But they're controversial, and most scientists prefer the dark matter hypothesis. But what if both explanations are wrong? What if the rotation curves are anomalous because the galaxies are being actively controlled? If a Type 3 civilization wanted to maintain a galaxy structure over billions of years, they would need to manage its rotation, adjusting the orbits of stars to prevent collisions and maintain stability. The rotation curves we observe might not be natural at all. They might be the signature of active galactic management, a kind of cosmic traffic control operating on timescales we can barely comprehend. Then there are the spiral arms themselves. Spiral galaxies are beautiful, with elegant arms that curve outward from the centre like a cosmic pinwheel. But according to our models, these arms shouldn't be permanent. Stars in a galaxy orbit at different speeds depending on their distance from the centre, which means the spiral pattern should wind up and disappear over time, like cream stirred into coffee. And yet spiral galaxies maintain their structure for billions of years. The standard explanation involves density waves, regions of higher density that move through the galaxy, triggering star formation and creating the appearance of spiral arms. It's a clever solution, but it requires very specific conditions. The waves have to be just right. The timing has to be perfect. It works mathematically, but it feels almost too convenient. What if the spiral arms are maintained artificially? What if a Type D civilization shapes them deliberately, using gravity manipulation or stellar engineering to create and preserve these patterns? The arms might serve a functional purpose. Perhaps they're optimized for energy collection, or they create stable zones where new stars can form under controlled conditions. From our perspective, they look like natural structures, but to the civilization that built them, they might be as deliberate as the streets of a city, laid out according to a plan we can't perceive. And then there's the question of galactic cores. At the centre of most galaxies, including our own, there's a supermassive black hole, an object millions or even billions of times more massive than our Sun, compressed into a region smaller than our solar system. These black holes are incredibly powerful, capable of producing jets of energy that stretch for thousands of light years. We think they formed naturally, growing over time as they consumed gas and stars. But black holes are also the ultimate power source. If you could harness the energy of a rotating black hole, you could power a civilization for billions of years. The process is called the Penrose process, and it's theoretically possible. You extract energy from the black hole's rotation, using it to power whatever you need. What if the supermassive black holes at the centres of galaxies aren't natural? What if they were built, or at least modified, to serve as galactic power plants? A Type 3 civilization would need an enormous, stable energy source, and a supermassive black hole fits the bill perfectly. The jets we observe might not be random emissions. They might be exhaust, the waste heat from a cosmic engine that's been running for billions of years. There's also the mystery of quasars, extremely bright objects found at the centres of distant galaxies, so luminous that they outshine all the stars in their host galaxies combined. We think quasars are powered by supermassive black holes actively consuming matter, heating it to millions of degrees and causing it to emit intense radiation. But quasars are strange. They're incredibly bright, but they're also incredibly distant, which means we're seeing them as they were billions of years ago. In the nearby universe, quasars are rare. It's as if they were common in the early universe and then mostly disappeared. What if quasars aren't natural phenomena, but the signatures of young Type 3 civilizations building their galactic infrastructure? The intense energy output might be the result of large-scale construction projects, civilizations harvesting matter from their galactic cores, building Dyson swarms around millions of stars, reshaping their galaxies into efficient energy-collecting machines. As the construction finishes and the systems become more efficient, the excess energy decreases and the quasar fades. By the time we see nearby galaxies, the construction is complete, and the civilizations have moved into a quieter, more stable phase of existence. It's speculation, of course, but it fits the observations, and it raises a haunting question. If the bright quasars we see in the distant universe are civilizations under construction, then what are the quiet galaxies nearby? Are they finished projects? Are they inhabited? Are we living inside one of them right now, surrounded by technology so advanced that we mistake it for nature? One of the most famous anomalies in modern astronomy is Tabby's star, officially known as Keck 8462852. Discovered by the Kepler Space Telescope, this star exhibits bizarre dimming patterns that don't match anything we've seen before. Most stars dim periodically when planets pass in front of them, blocking a small fraction of their light. But Tabby's star dims irregularly, sometimes by as much as 20%, and the dimming events don't repeat on a predictable schedule. Something is blocking the star's light, but it's not a planet. It's something much larger and much stranger. When the discovery was announced, one of the proposed explanations was a Dyson swarm, a collection of artificial structures orbiting the star, built by an advanced civilization to harvest its energy. The idea captured the public imagination. Could we finally have found evidence of alien technology? Astronomers pointed their instruments at the star, searching for radio signals or other signs of intelligence. They found nothing conclusive. Eventually other explanations emerged. Perhaps the dimming is caused by a cloud of dust or a swarm of comets, or some other natural phenomenon we don't fully understand. But the question lingers. If we did find a Dyson sphere, would we recognise it? Would we be able to distinguish it from a natural object? A mature Dyson swarm, built by a civilization that's had millions of years to refine its technology, might be nearly invisible. It might emit very little waste heat, or radiate in wavelengths we're not monitoring. It might be designed to look natural, to avoid attracting attention from younger civilizations like ours. And if a single star can be surrounded by artificial structures, why not an entire galaxy? If a Type 2 civilization can build a Dyson sphere, then a Type 3 civilization can build a Dyson galaxy, a collection of billions of stars, each one surrounded by energy collectors, all linked together into a single unified system. From the outside, it would look like a normal galaxy. But inside, every star would be a power plant, every planet a factory, every cubic light year of space filled with invisible infrastructure. We might be living in one right now. The Milky Way might be a machine, and we might be too small, too young, too primitive to see it. We look at the stars and see nature. But what if we're looking at technology, ancient, patient, incomprehensibly vast technology that's been running since before our planet existed? This brings us to the Fermi paradox, one of the most troubling questions in all of science. If the universe is so vast and if life is even remotely common, then where is everyone? Why haven't we detected any signs of alien civilizations? Why does the cosmos seem so empty? There are many proposed solutions to the paradox. Maybe life is rare. Maybe intelligent life is even rarer. Maybe civilizations destroy themselves before they can spread to the stars. Maybe they're out there, but they're too far away for us to detect. Maybe they're deliberately hiding. Maybe they're here, but we don't recognize them. Or maybe they're everywhere, and we're looking right at them without realizing it. If galaxies are megastructures, then the universe isn't empty at all. It's full of civilizations, billions of them, each one inhabiting a galaxy they've reshaped to suit their needs. They're not hiding, they're in plain sight. We just don't recognize them because their technology is so advanced that it looks like nature. This is sometimes called the zoo hypothesis or the planetarium hypothesis. The idea that advanced civilizations are aware of us but choose not to make contact, either because they're studying us or because they're waiting for us to reach a certain level of development. But there's a darker version of this idea. What if they're not waiting? What if they simply don't care? What if we're so far beneath their notice that they don't even register our existence? Imagine you're walking through a forest. You're aware on some level that the forest is full of life. Insects, bacteria, fungi, all going about their business. But you don't stop to communicate with them. You don't try to make contact with the ants or explain yourself to the trees. You're not hostile. You're not even indifferent. You're simply operating on a different scale with different concerns. The ants might as well be part of the landscape. Now imagine a Type 3 civilization, billions of years old with technology that spans an entire galaxy. What would we be to them? We've been broadcasting radio signals for less than a century. We've barely left our own planet. We're not even a Type 1 civilization yet. To a Type 3 civilization, we might be less significant than ants. We might be background noise, a brief flicker of activity in a galaxy they've been managing for eons. And if that's true, then the Fermi paradox isn't a paradox at all. The aliens aren't missing. They're the galaxies themselves. They're the structures we've been studying for decades, cataloguing and measuring and trying to understand. We've been looking for radio signals and spacecraft, but we should have been looking at the architecture of the cosmos itself. There's another layer to this mystery, one that takes us even deeper into the unknown. If galaxies can be artificial, then what about larger structures? What about galaxy clusters, or superclusters, or the cosmic web itself? The universe, when viewed on the larger scales, looks like a web. Galaxies cluster together along filaments of dark matter, separated by vast voids where almost nothing exists. The filaments stretch for hundreds of millions of light years, connecting galaxy clusters like threads in a cosmic tapestry. It's one of the most beautiful structures in nature, elegant, intricate, almost organic. But it's also suspiciously regular. The cosmic web follows mathematical patterns. The distribution of galaxies isn't random, it's structured, organised, almost as if it were designed. Computer simulations can recreate the web by starting with the conditions of the early universe and letting gravity do its work. The simulations match observations remarkably well, but they also require very specific initial conditions. The early universe had to be almost perfectly smooth, with just the right amount of variation to allow structures to form. If the conditions had been even slightly different, the cosmic web wouldn't exist. The universe would be either completely uniform or completely chaotic. This is sometimes called the fine-tuning problem. The laws of physics, the constants of nature, the initial conditions of the universe, all of them seem to be precisely calibrated to allow the formation of stars, galaxies, and ultimately life. Change any one of them by a tiny amount, and the universe becomes sterile. No stars, no planets, no life. Just an endless expanse of hydrogen gas, or a brief flash of energy that collapses back into nothing. Some scientists explain this with the anthropic principle, the idea that we observe a fine-tuned universe because we couldn't exist in any other kind. If the universe weren't fine-tuned, we wouldn't be here to notice. It's a tautology, but it's also unsatisfying. It doesn't explain why the universe is fine-tuned, only why we observe it to be. Others invoke the multiverse, the idea that there are countless universes, each with different laws and constants, and we happen to live in one of the rare ones that allows life. It's an elegant solution, but it's also untestable. We can't observe other universes, so we can't prove they exist. But there's a third possibility, one that's rarely discussed in mainstream science. What if the universe is fine-tuned because it was tuned? What if the initial conditions weren't random but chosen? What if the Big Bang itself was an act of engineering? This is the ultimate megastructure. Not a galaxy, not a cluster, but the entire universe. A cosmos designed from the beginning to produce stars, galaxies, and life. A cosmic machine set in motion billions of years ago by a civilization so advanced that they could manipulate the fundamental constants of reality itself. It sounds like science fiction. It sounds like theology. But it's also a logical extension of the Kardashev scale. If a Type 3 civilization can reshape a galaxy, then what comes next? Type V as Type B. Civilizations that can manipulate the fabric of space-time, that can create pocket universes, that can engineer the laws of physics themselves. And if such a civilization existed, what would their universe look like? It would look exactly like ours. Vast, ancient, filled with galaxies and stars governed by mathematical laws that allow complexity to emerge. It would look natural, but it would be designed, every atom and every photon placed according to a plan we can't begin to comprehend. Let's return to something more immediate, something we can almost touch. Let's talk about the stars themselves. Every star we see in the night sky is a nuclear furnace, fusing hydrogen into helium and releasing energy in the process. This process is well understood. We can calculate how long a star will live based on its mass, predict when it will die, model its evolution from birth to death. Stars are natural objects, formed when clouds of gas collapse under their own gravity. This is basic astrophysics, confirmed by countless observations. But stars are also incredibly useful. They're stable, long-lived sources of energy. A star like our Sun will burn for about 10 billion years, providing a steady output of light and heat. If you were a Type 2 civilization, you would want to harvest that energy. And if you were a Type 3 civilization, you would want to optimize it, modify the star to burn more efficiently, extend its lifespan, increase its output. Is it possible to modify a star? In theory, yes. You could inject heavier elements into the core to change the fusion rate. You could remove mass to make the star burn more slowly. You could surround it with mirrors to redirect its light. You could even build artificial stars, fusion reactors the size of planets, designed to produce energy on demand. And if you did this across an entire galaxy, modifying billions of stars to serve your needs, what would it look like from the outside? It would look like a galaxy. A perfectly normal natural galaxy, unless you looked very closely and noticed that the stars were burning a little too steadily, lasting a little too long, distributed a little too evenly. There are stars that don't quite fit our models. Stars that are too bright for their mass or too dim. Stars with unusual chemical compositions or strange pulsation patterns. Most of these anomalies can be explained with additional physics. Maybe the star is part of a binary system, or maybe it's surrounded by a dust cloud, or maybe our models are slightly wrong. But what if some of them can't be explained? What if some of them are artificial? In 2015, astronomers discovered a star called SDSS J14+35, which has an unusual chemical composition. It contains almost no heavy elements, no carbon, no oxygen, no iron. It's made almost entirely of hydrogen and helium, as if it formed in the very early universe before any heavy elements existed. But it's not in the early universe. It's here, now, in our galaxy. How did it survive for billions of years without accumulating heavier elements from its surroundings? One possibility is that it's a remnant from the early universe, somehow preserved in pristine condition. Another possibility is that it's artificial, a star built by a civilization that wanted a pure hydrogen fusion reactor, free from the contamination of heavier elements. We can't prove it, we probably never will. But the question remains, how many of the stars we see are natural, and how many are machines? And what about us? What about Earth, and humanity, and our place in all of this? If galaxies are megastructures, if the universe is filled with ancient civilizations operating on scales we can barely imagine, then what are we? Are we an accident? A random byproduct of natural processes that happen to occur in a corner of an artificial galaxy? Or are we intentional? Are we part of the design? There's a concept in philosophy called the simulation hypothesis, which suggests that we might be living in a computer simulation created by an advanced civilization. The idea has gained traction in recent years, popularised by philosophers like Nick Bostrom and technologists like Elon Musk. The argument goes like this. If it's possible to create realistic simulations of conscious beings, and if advanced civilizations are likely to create many such simulations, then statistically speaking, we're more likely to be living in a simulation than in base reality. The hypothesis is controversial, and many scientists dismiss it as unfalsifiable speculation, but it connects to the idea of galactic megastructures in an interesting way. If a Type 3 civilization can reshape a galaxy, they can certainly create simulations. They might run countless simulations of galactic evolution, testing different configurations, exploring different possibilities, and some of those simulations might include conscious beings, simulated civilizations that believe they're real, that look up at their simulated sky and wonder if they're alone. Are we one of those simulations? Are we living in a model, a test run, a sandbox created by beings who are trying to understand how galaxies evolve? It's impossible to know, but if we are, then the galaxy we see around us isn't just artificial, it's virtual. The stars aren't real. The planets aren't real. We aren't real, at least not in the way we think we are. But even if we're not in a simulation, even if we're living in base reality, the question remains, why are we here? If the galaxy is a machine, what's our role in it? Are we the engineers destined to one day reach Type D status and take control of the structure we inhabit? Are we the maintenance crew meant to keep the machine running? Are we the observers, placed here to witness and record? Or are we irrelevant, a side effect of processes that have nothing to do with us? There's a strange comfort in the idea that we might be irrelevant. It means we're free. If the galaxy is a machine and we're not part of its purpose, then we can define our own purpose. We can explore, create, build, dream. We can reach for the stars not because we're supposed to, but because we choose to. But there's also a strange terror in it. If we're irrelevant, then nothing we do matters on a cosmic scale. Our civilizations will rise and fall, our planet will eventually be consumed by the sun, our galaxy will collide with Andromeda in a few billion years, and the machine will keep running, indifferent to our existence, unless we become part of it. Unless we grow up, reach Type 1, then Type 2, then Type 3. Unless we learn to reshape stars and galaxies, to think in terms of billions of years and trillions of lives, unless we become the architects ourselves. There's one more piece to this puzzle, one more layer of mystery that we need to explore before we can rest. If galaxies are artificial, then who built them? Where did the builders come from? And what happened to them? One possibility is that they're still here, still managing their galaxies, still operating on timescales so vast that we can't perceive their actions. They might be watching us right now, observing our development, waiting to see if we'll survive long enough to join them. Or they might not even be aware of us, focused on projects and concerns that are completely beyond our understanding. Another possibility is that they're gone. Civilizations, no matter how advanced, might not last forever. They might destroy themselves in wars or ecological collapse. They might transcend physical reality, uploading themselves into digital substrates or ascending to higher dimensions. They might simply lose interest, abandoning their galaxies to run on autopilot while they move on to other pursuits. If the builders are gone, then the galaxies we see might be ruins. Ancient machines still running, still following their programming, but no longer guided by conscious minds. The universe might be full of these ghost structures, relics of civilizations that rose and fell billions of years ago, leaving behind only their architecture. There's something deeply melancholy about this idea. Imagine a galaxy that was once home to trillions of beings, a thriving civilization that spanned thousands of light years and lasted for millions of years. They built wonders we can't imagine, artificial worlds, stellar engines, structures that bent space-time itself. And then, for whatever reason, they disappeared. The machines kept running, the stars kept burning. But the minds that created it all were gone, leaving behind only silence. And now we're here, looking up at their creation, trying to understand what it is. We're like children exploring an abandoned city, marveling at the buildings and wondering who built them. We don't have the context to understand what we're seeing. We don't know the language, the culture, the purpose. We can only guess. But maybe that's enough. Maybe the act of wondering, of asking questions, of reaching toward the unknown, maybe that's what makes us worthy of inheriting the machine. Maybe the builders, wherever they are waiting for us to figure it out. Waiting for us to realize that the galaxy isn't just our home, it's our inheritance. But let's be rigorous for a moment. Let's step back from the poetry and the speculation and ask the hard questions. What would it actually take to build a galaxy? What kind of resources, what kind of time, what kind of technology would be required? The numbers are staggering. A single star like our Sun contains about 2 Warks 1030 kilograms of matter. That's a 2 followed by 30 zeros. The Milky Way contains somewhere between 200 and 400 billion stars, plus vast clouds of gas and dust, plus the mysterious dark matter that makes up most of the galaxy's mass. The total mass is roughly 1.5 trillion times the mass of the Sun. That's 3 × 10 + 42 kilograms, 3 million trillion kilograms. To move that much matter, to arrange it into the spiral structure we observe, to maintain that structure over billions of years, it seems impossible. The energy requirements alone would be astronomical. Every time you move a star, you're working against gravity on a cosmic scale. You'd need to expend energy equivalent to the star's entire lifetime output just to shift it a few light years. And yet, the universe has been doing something similar for billions of years through natural processes. Stars do move, galaxies do evolve. The difference is time scale. Natural galactic evolution happens over hundreds of millions or billions of years. Gravity works slowly, but it works for free. An advanced civilization wouldn't be working against the laws of physics. They'd be working with them, using gravity as a tool, nudging stars into desired orbits and letting time do the rest. Consider gravitational assists, which we already use in space exploration. When we send a probe to the outer solar system, we don't just point it in the right direction and fire the engines. We swing it past planets, using their gravity to change the probe's trajectory and speed without burning fuel. It's elegant, efficient, and it works because we're patient. We're willing to wait years for a spacecraft to reach its destination if it means conserving energy. Now scale that up. A Type 3 civilization would have mastered gravitational engineering on scales we can't imagine. They wouldn't need to physically push stars around, they'd create gravitational gradients, use carefully positioned masses to alter stellar orbits over millions of years. A star here moved slightly inward, a star there nudged into a higher orbit. Over time, the cumulative effect would reshape the entire galaxy, and they'd have time. So much time. If a civilization lasts for 1 billion years, and why shouldn't it? If they've solved the problems of war, resource scarcity, and existential risk, then projects that take 10 million years are routine. They're not monumental undertakings. They're just work, the normal business of civilization. From their perspective, building a galaxy might not be any more impressive than us building a city. Yes, it's complex. Yes, it requires planning and coordination and vast resources, but it's doable. It's just engineering. The mathematics, when you work through them, don't actually forbid it. The energy is available, every star is a power source. The materials are available. Every gas cloud, every asteroid belt, every dead world is raw material. The time is available. The universe is 13 billion years old, and it will be around for trillions more. The only question is whether anyone has the will, the patience, and the longevity to attempt it. And if the answer is yes, if even one civilization anywhere in the universe decided to try, then what we're looking at when we look at galaxies might not be nature at all. So let's talk about detection. If galaxies can be artificial, how would we actually prove it? What would constitute evidence strong enough to overturn the standard cosmological model and convince the scientific community that we're living in an engineered universe? The challenge is that we need to find something that can't be explained by natural processes. An anomaly so specific, so precise, so obviously intentional that it can only be the result of intelligence. In the search for extraterrestrial intelligence, or CT, researchers look for narrowband radio signals, frequencies that don't occur naturally that can only be produced by technology. We need something similar for galaxies, a signature that screams artificial. One possibility is symmetry. Nature tends towards symmetry in some contexts, crystals, snowflakes, orbits. But on galactic scales, things are usually messy. Galaxies collide and merge, creating irregular shapes. Gas clouds clump unevenly. Star formation happens in bursts and clusters. There's order, yes, but it's statistical order, not geometric precision. But what if we found a galaxy that was too symmetrical? A spiral with arms that were exactly evenly spaced, that maintained perfect mathematical proportions as they curved outward. A galaxy where the stars were distributed in a pattern that followed a clear formula, like points on a grid or nodes on a network. We've found some galaxies that are remarkably symmetrical, actually. NGC 1300, a barred spiral galaxy about 61 million light-years away, has an almost perfect geometric structure. 2 straight bars of stars extending from the centre, with spiral arms curving off at precise angles. It's beautiful, and it fits our models of barred spiral formation. But it's also just on the edge of being too perfect. A little more symmetry, a little more precision, and we'd have to start asking uncomfortable questions. Then there's the question of energy efficiency. A natural galaxy wastes energy. Stars radiate in all directions, sending light and heat out into the void, where most of it will never be absorbed or used. Supernovae explode with incredible violence, scattering heavy elements across thousands of light years. Black holes devour matter and spit out jets of high-energy particles that serve no obvious purpose. But an artificial galaxy would be optimized. It would capture and use energy efficiently. Stars might be surrounded by Dyson swarms that intercept most of their light. Supernovae might be prevented or controlled, their energy harvested rather than wasted. Black holes might be equipped with Penrose process extractors, converting their rotational energy into usable power. So we should look for galaxies that are too efficient. Galaxies that emit less waste heat than expected, that have fewer supernovae, that show evidence of large-scale energy collection. This is tricky because we don't have a perfect model of what normal efficiency looks like. But statistical analysis might reveal outliers, galaxies that are significantly more efficient than the average, in ways that can't be explained by natural variations. There's also the possibility of deliberate signals. If a Type 3 civilization wanted to announce its presence, it could encode information in the structure of its galaxy. Patterns in the distribution of stars, ratios in the spacing of spiral arms, frequencies in the pulsations of variable stars. These patterns would be detectable to anyone with telescopes and computers, but they'd be subtle enough that they wouldn't interfere with the galaxy's function as a megastructure. Some researchers have proposed looking for mathematical constants embedded in cosmic structures. The ratio of a galaxy's rotation speed to its diameter, for example, or the distribution of star types in the galactic core. If these values corresponded to mathematical constants like pi, e, or the golden ratio with unusual precision, it might be evidence of design. Carl Sagan explored this idea in his novel Contact, where aliens embed a message in the digits of pi itself, a sequence of ones and zeros that, when arranged in a grid, form a geometric pattern. It's fiction, but the principle is sound. If you want to leave a message that will last forever and be recognised by any technological civilization, you embed it in mathematics. And if you're building a galaxy, you have a very large canvas to work with. Here's the unsettling part. We've already found anomalies, lots of them. Most have been explained, or at least explained away, but some remain deeply puzzling. Take the WOW signal, detected in 1977 by Ohio State University's Big Ear radio telescope. It was a narrow-band radio signal that lasted 72 seconds, far stronger than the background noise coming from the direction of the constellation Sagittarius. It had all the characteristics of an artificial signal. Astronomer Jerry Eman, who discovered it, circled the data on the printout and wrote "WOW" in the margin. The signal has never been detected again, despite decades of follow-up observations. The standard explanation is that it was probably terrestrial interference, or perhaps a natural phenomenon we don't understand. But we don't actually know. It could have been a signal from an artificial source that was only transmitting briefly, or that was moving, or that was aimed in a slightly different direction when we looked again. Then there's the fast radio bursts, or FRBs, intense pulses of radio waves that last just milliseconds, but release as much energy as the sun emits in days. They come from distant galaxies, billions of light years away. We've detected dozens of them, and we still don't know what causes them. The leading natural explanation involves magnetars, neutron stars with incredibly powerful magnetic fields, but some FRBs repeat in patterns that seem almost too regular to be random. One, designated FRB Steinply of 2, repeats every 157 days. Another shows a 16-day cycle. Are these natural phenomena? Probably. Neutron stars can have regular rotation periods, but they could also be artificial. They could be beacons, lighthouses sweeping across the cosmos, announcing the presence of civilizations. Or they could be byproducts of massive energy transfers, the exhaust from galactic-scale power systems. And then there are the cosmic voids, vast regions of space where galaxies are strangely absent. The largest known void, the Botas void, is about 330 million light-years across and contains far fewer galaxies than expected. It's not completely empty. There are about 60 galaxies in a space that should contain 2,000, but it's eerily vacant. The standard explanation involves the cosmic web. Galaxies cluster along filaments of dark matter, and the spaces between the filaments are naturally empty. But the Botas void is so large and so empty that it's right at the edge of what our models predict. Some researchers have suggested it might be evidence of some unknown cosmological process. Others have even speculated, half-jokingly, that it could be a region that's been cleared out by a civilization that's building something too large for us to comprehend. Imagine a Type 4 civilization, one that's moved beyond galactic engineering to work on the structure of the universe itself. What would they build? What would a cosmic construction project look like? Maybe it would look like a void, a cleared space where matter has been harvested and repurposed, leaving behind only emptiness. It sounds absurd. It probably is absurd. But the void is there, and we don't have a perfect explanation for it. Let's return to the Fermi paradox, because it's central to everything we're discussing. The paradox is usually framed as a question about detection. Why haven't we seen any signs of alien civilizations? But maybe we're asking the wrong question. Maybe the question should be, why would we expect to see them? Think about it from the perspective of an advanced civilization. You've been around for millions or billions of years. You've spread across your galaxy, building megastructures, harvesting stars, creating a civilization that spans thousands of light years. You're aware that the universe might contain other intelligent species, younger ones, primitive ones like the humans on that little planet, orbiting a yellow dwarf star in the outer arm of the galaxy. Do you announce yourself? Do you send signals, broadcast your location, make yourself obvious? Maybe not. Maybe you've learned, over the eons, that broadcasting your presence is dangerous. Maybe you've encountered hostile civilizations, or witnessed them destroy each other, and you've concluded that the smart strategy is to stay quiet, to blend in, to make your technology look natural so that younger civilizations can't find you until they're advanced enough to be worth meeting, or advanced enough to be a threat. This is sometimes called the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin. The idea is that the universe is like a dark forest at night, full of hunters hiding in the shadows. Everyone is silent because making noise attracts attention, and attention means death. It's a bleak vision, but it's also logical. If resources are finite and civilizations are competitive, then stealth becomes a survival strategy. But there's a less paranoid version of this idea. Maybe civilizations don't hide because they're afraid. They hide because they're polite, because they've seen what happens when an advanced civilization contacts a primitive one. The primitive civilization is disrupted, transformed, sometimes destroyed, not through malice, but through sheer cultural weight. The contact changes everything. If you're a Type 3 civilization, you might decide that the ethical thing to do is to let younger civilizations develop on their own. You don't interfere. You don't make contact. You just watch and wait and hope that they survive long enough to join you. And in the meantime, you design your technology to be invisible, to blend seamlessly with natural phenomena so that the younger civilizations can look out at the universe and see a cosmos governed by physics, not by ancient minds. This would explain both the Fermi paradox and the possibility of artificial galaxies. The civilizations are there, the megastructures are there, we're looking right at them, but they're designed to be undetectable until we're ready. And how will they know when we're ready? Maybe when we start asking the right questions. Maybe when we start looking at galaxies and wondering if they might be artificial. Maybe the very act of conceiving this idea, of taking it seriously enough to search for evidence, is the test. The civilizations are waiting to see if we're clever enough, curious enough, open-minded enough to notice what's hidden in plain sight. Before we go further, we should acknowledge the elephant in the room. This entire hypothesis might be completely wrong. The vast majority of astronomers and cosmologists believe that galaxies are natural structures, formed through well-understood physical processes. The evidence for this is overwhelming. We can model galaxy formation on computers and get results that match observations. We can trace the evolution of galaxies over billions of years by looking at distant objects and seeing them as they were in the past. We can measure the cosmic microwave background radiation, the afterglow of the Big Bang, and see the tiny density fluctuations that seeded the formation of galaxies. The standard model of cosmology works. It makes predictions that are confirmed by observation. Is one of the greatest intellectual achievements in human history. To propose that galaxies might be artificial is to challenge all of that. It's to suggest that the scientific consensus is fundamentally mistaken, that we've been fooled by a phenomenon so advanced that we can't recognize it as technology. That's an extraordinary claim, and extraordinary claims require extraordinary evidence, and right now we don't have that evidence. We have anomalies, yes. We have mysteries and unanswered questions. But anomalies are not proof. Every scientific theory has loose ends, observations that don't quite fit, phenomena that require additional explanation. That's normal. That's how science works. You don't overturn an entire model just because there are a few things you don't fully understand. So it's entirely possible, probable even, that galaxies are exactly what they appear to be. Natural structures formed by gravity and time. The rotation curves are explained by dark matter, which will eventually be detected in laboratories. The spiral arms are maintained by density waves, which we'll understand better as our simulations improve. The fine-tuning of the universe is explained by the anthropic principle or the multiverse. The Fermi paradox is explained by the rarity of life, or the difficulty of interstellar travel, or any number of other factors. But even if the probability is small, even if the idea seems absurd, even if every scientist in the world rolls their eyes at the suggestion, it's still worth asking the question. Because if we're right, if galaxies are artificial, then everything changes. Our understanding of the universe, our place in it, our future as a species, all of it is transformed. And if we're wrong, then we've still learned something. We've explored the boundaries of what's possible. We've asked a question that no one else thought to ask. We've reminded ourselves that the universe is stranger and more wonderful than we can imagine, and that we should always be willing to question our assumptions. Science progresses not just by confirming what we believe, but by challenging it, by asking what if, and following the question wherever it leads, even if it leads to places that seem ridiculous at first. Some of the greatest discoveries in history started with ideas that seemed absurd. Continental drift, quantum mechanics, the Big Bang itself. They all sounded crazy until the evidence became undeniable. So let's keep asking, let's keep looking, and let's be honest enough to admit that we might be wrong about everything. Suppose we decide to take this seriously. Suppose we want to actively search for evidence that galaxies might be artificial. What would that search look like? What tools would we need? What strategies would we employ? First, we'd need better telescopes, much better. The James Webb Space Telescope, launched in 2021, can observe galaxies as they appeared more than 13 billion years ago, just a few 100 million years after the Big Bang. It can analyse the chemical composition of exoplanet atmospheres, search for biosignatures, study the formation of stars and galaxies in unprecedented detail. But even JWST has limitations. It can't resolve individual stars in distant galaxies. It can't detect the subtle signatures of Dyson spheres or stellar engineering on a galactic scale. We'd need telescopes with larger apertures, better resolution, and the ability to observe in multiple wavelengths simultaneously. We'd need space-based observatories that can operate continuously without interference from Earth's atmosphere or radio noise. We'd need networks of telescopes working in coordination, using interferometry to achieve resolution equivalent to a single telescope the size of a planet, or even a solar system. Some of these projects are already in development. The extremely large telescope, being built in Chile, will have a primary mirror 39 meters across, 5 times larger than any existing optical telescope. The Square Kilometre Array, a radio telescope network spanning multiple continents, will have a collecting area of 1 square kilometre and sensitivity far beyond anything we've built before. The Lunar Crater Radio Telescope, a proposed project that would build a massive radio dish inside a crater on the far side of the Moon, would be shielded from Earth's radio interference and could detect signals from the cosmic dark ages before the first stars formed. With these instruments, we could conduct systematic surveys of galaxies, looking for anomalies. We could measure rotation curves with greater precision, searching for deviations from the dark matter model. We could analyse the distribution of stars within galaxies, looking for patterns that are too regular or too precise to be natural. We could monitor individual stars for unusual behaviour, dimming patterns that suggest Dyson swarms, spectral signatures that indicate stellar engineering, like curves that encode information. We'd also need better computational tools. The amount of data generated by modern telescopes is staggering. The Square Kilometre Array, once completed, will generate more data in a single day than the entire internet. Analysing that data, searching for subtle patterns and anomalies, requires machine learning algorithms and artificial intelligence systems capable of recognizing phenomena that we haven't explicitly programmed them to look for. This is already happening, actually. Astronomers are using AI to classify galaxies, identify exoplanets, discover gravitational lenses, and detect fast radio bursts. The algorithms are getting better, learning to spot patterns that human observers might miss. Eventually, we might deploy AI systems specifically designed to search for evidence of artificial structures, systems trained to recognize the signatures of technology, to distinguish between natural and engineered phenomena, to flag anything that seems suspiciously intentional. And we'd need theoretical work. We'd need physicists and engineers to work out what artificial galaxies would actually look like, what signatures they'd produce, what laws of physics would constrain their design. We'd need to build models and simulations exploring the possibility space of galactic engineering. What would a galaxy look like if it were optimized for energy collection? What if it were designed as a habitat for trillions of beings? What if it were built as a work of art, a cosmic sculpture meant to be beautiful? This kind of speculative engineering is sometimes dismissed as science fiction, but it's valuable. It helps us think outside the box, to imagine possibilities we wouldn't otherwise consider. And sometimes the speculations turn out to be true. Freeman Dyson's proposal for stellar energy collection was initially theoretical, but now we actively search for Dyson spheres. Gerard O'Neill's designs for space habitats were science fiction in the 1970s, but now we're seriously considering building them. The line between science fiction and science has always been blurry, and that's a good thing. But there's another obstacle to this search, one that's harder to overcome than technological limitations. It's psychological. It's the difficulty of accepting that we might be wrong about something so fundamental. Humans have a strong bias toward believing that our current understanding of the world is basically correct. It's called the normalcy bias, and it's a survival mechanism. In daily life, it's useful to assume that the world will keep working the way it always has, that the patterns we've observed will continue. But in science, normalcy bias can be dangerous. It makes us resistant to paradigm shifts, skeptical of ideas that challenge our assumptions, dismissive of evidence that doesn't fit our models. History is full of examples. When Alfred Wegener proposed continental drift in 1912, the idea that continents could move across the Earth's surface, he was ridiculed. The mechanisms he proposed were wrong, but the basic idea was correct. It took 50 years and the discovery of seafloor spreading before the scientific community accepted plate tectonics. When Barbara McClintock discovered jumping genes, genetic elements that could move within the genome, her work was ignored for decades because it didn't fit the prevailing model of how genetics worked. She eventually won a Nobel Prize, but only after years of being dismissed by her peers. The idea that galaxies might be artificial faces a similar barrier. It contradicts everything we've been taught, everything we've built our understanding of the cosmos upon. It's easier to dismiss it as pseudoscience or fringe speculation than to take it seriously. And most of the time, that instinct is correct. Most fringe ideas are wrong, but not all of them. So how do we overcome this bias? How do we stay open-minded without becoming credulous? How do we investigate ideas that seem absurd without wasting time on ideas that are absurd? The answer is evidence. We follow the evidence wherever it leads, even if it leads somewhere uncomfortable. We design experiments and observations that can distinguish between hypotheses. We make predictions and test them. We remain skeptical, but we also remain curious. We remember that the universe doesn't care about our assumptions, and that nature has surprised us before and will surprise us again. And we remember that asking the question doesn't mean we believe the answer. We can explore the possibility that galaxies are artificial without committing to the idea. We can say, I don't know, but let's find out, instead of that's impossible or that must be true. Science thrives in the space between certainty and ignorance, in the zone where we're willing to investigate ideas that might be wrong, but might also change everything. Let's imagine, for a moment, that we do find evidence. Not conclusive proof, necessarily, but strong enough evidence that the scientific community starts taking the idea seriously. A pattern in galactic structures that can't be explained naturally. An energy signature that looks like large-scale engineering. A signal embedded in the cosmic microwave background that spells out the first 1,000 digits of pi. What happens next? The first reaction would be shock, disbelief. Scientists would scramble to find alternative explanations, to poke holes in the evidence, to replicate the observations. The media would explode with speculation. Religions would grapple with the theological implications. Governments would convene panels and committees. The discovery would dominate every conversation, every news cycle, every social media feed. And then, gradually, the shock would fade. We'd begin to process what it means. We'd start to understand that we're not alone, that we've never been alone, that the universe has been inhabited by intelligences far older and more powerful than us for billions of years, that we're living inside a structure they built, walking on a planet that exists because they arranged the stars in a way that allowed solar systems to form. Some people would find this comforting. The universe isn't cold and empty after all. There are others out there, and they've achieved things we can barely imagine. We have something to aspire to, a future to work toward. If they did it, we can do it too. Others would find it terrifying. We're not special. We're not even significant. We're insects crawling through the machinery of beings that might not even notice we exist. Everything we've built, everything we've achieved, is trivial compared to what they've done. We're children playing in a sandbox that someone else built, and we didn't even realize it. And some would find it liberating. The pressure is off. We don't have to figure everything out on our own. We don't have to save ourselves from extinction or solve all the problems of civilization or reach the stars before our sun dies. Someone else has already done it. They've built a galaxy that will last for billions of years. All we have to do is survive long enough to understand what we're part of. But regardless of how we feel about it, the practical implications would be enormous. Every field of science would be transformed. Astrophysics would need to distinguish between natural and artificial phenomena in every observation. Biology would need to consider the possibility that life on Earth was influenced or even seeded by the builders. History and anthropology would need to re-examine human development, asking whether we've been subtly guided or monitored. Philosophy would grapple with questions of purpose and meaning in a universe where we're not the pinnacle of creation but the newcomers. And then there's the question of what we do with the knowledge. Do we try to make contact with the builders? Do we search for ways to communicate with entities that might be billions of years ahead of us technologically? Do we try to prove ourselves worthy of their attention? Or do we intentionally stay quiet, afraid of what might happen if they notice us? Or do we just keep doing what we're doing? Keep building, keep exploring, keep learning, keep trying to survive and grow and reach for the stars, knowing now that we're following a path that others have walked before us. Knowing that the goal isn't just to reach the stars, but to understand the structures they're embedded in, to learn the technology that makes galaxies work, to eventually take our place among the builders. If galaxies are megastructures, then humanity's future isn't about conquering space. It's about learning to read the universe as a text, as a message left for us to decode. Every star becomes a data point. Every galaxy becomes a lesson. We stop thinking of the cosmos as a resource to be exploited and start thinking of it as a library, a museum, a university where the curriculum spans billions of years and the textbooks are written in the structure of matter itself. Our first step is to become a Type 1 civilization. We need to master our own planet, harness its energy without destroying it, solve the problems of war and poverty and environmental collapse. This is the filter that most civilizations probably fail. It's the most dangerous transition, the point where a species gains the power to destroy itself and has to choose not to. We're in the middle of that transition right now. Whether we survive it is still an open question. If we do survive, if we reach Type 1 status, then the next step is to spread beyond Earth. Not in a rush, not in a desperate scramble for resources, but deliberately, carefully, learning as we go. We build habitats in orbit, on the Moon, on Mars. We mine asteroids and harness the energy of the Sun. We become a species that thinks in terms of the solar system, not just a single planet. And then, slowly, we reach for the stars. Not with generation ships or faster-than-light drives, those might be impossible, but with patience. We send probes to nearby systems, learn about the planets there, understand the local conditions. Eventually we might send humans, or posthumans, or AI systems that carry the essence of human civilization, even if they don't have biological bodies. As we expand, we look for the patterns. We study the stars we encounter, searching for signs of engineering. We analyse the structure of the galaxy, looking for the invisible infrastructure that might surround us. We try to understand how the machine works, what it's for, who built it. And maybe, after millions of years, after we've spread across thousands of star systems and built our own megastructures, we start to understand. We see the design. We recognise the signatures of the builders. We realise that they left clues for us, breadcrumbs scattered across the galaxy, waiting for us to be smart enough to find them. And then finally we make contact. Not because they reach out to us, but because we reach out to them. Because we've proven that we can survive, that we can grow, that we can think on the timescales and spatial scales required to be part of the cosmic community. We knock on the door, and they answer, and they welcome us home. This is the optimistic scenario. The universe as a great becoming, a process of civilizations rising and joining the builders, adding their own contributions to the galactic architecture. Humanity's future isn't extinction or stagnation, it's transformation. We become something greater than we are, not by transcending our humanity, but by extending it, by applying human curiosity and creativity to problems on a cosmic scale. But there's a darker possibility. What if the builders are gone and the galaxies are just running? What if we're not living in an active civilization's territory, but in its ruins? What if the machines are still operating, still following their programming, but no one is home? The lights are on, but nobody's watching. This would explain a lot. It would explain why we don't detect any signals, why there's no obvious communication, why the cosmos seems so silent. The civilizations that built these structures rose and fell billions of years ago. They left their creations behind, but they're gone now. Transcended, extinct, moved on to other universes, it doesn't matter. The result is the same. We're alone, surrounded by the machinery of gods who no longer exist. In this scenario, humanity's future is very different. We're not trying to join a cosmic community. We're trying to inherit it. We're the new tenants moving into an abandoned mansion, trying to figure out how everything works, hoping that we can maintain the systems that keep the lights on. This is both terrifying and exhilarating. Terrifying because it means we're truly alone, with no guidance, no help, no one to ask for advice. If we make a mistake, if we break something in the galactic machinery, there's no one to fix it. We're responsible for maintaining a system we don't fully understand, a system that's been running for billions of years and might stop if we're not careful. But it's also exhilarating because it means the galaxy is ours, not by conquest but by default. We're the inheritors of the greatest engineering project in history, and it's up to us to figure out what to do with it. Do we preserve it as it is, maintaining the machine out of respect for its builders? Do we modify it, adapting it to our own needs and purposes? Do we build our own megastructures alongside the ancient ones, adding new layers to the architecture? In this scenario, humanity's destiny is to become the new builders, not because we're following in anyone's footsteps, but because there's no one else to do it. We're the first intelligence to arise in this galaxy, since the ancients disappeared. And if we want the galaxy to remain inhabited, to continue being more than just a machine running on autopilot, then we need to step up. We need to grow into the role that was left vacant. It's a heavy burden, but it's also an opportunity, a chance to shape the future on the largest possible scale, to ensure that the galaxy becomes a place of life and consciousness and meaning, rather than just a dead engine consuming stars. Let's zoom back, out to the biggest questions. What does it mean for existence, for consciousness, for the nature of reality, if galaxies are artificial? It changes everything about how we understand purpose. In the standard materialist view, the universe has no inherent purpose. It just exists, following physical laws, and any meaning we find is meaning we create. We're cosmic accidents, patterns of matter that happen to be self-aware, and when we die, we're gone. And eventually the universe will end in heat death or a big rip or some other form of cosmic dissolution. But if galaxies are artificial, then the universe contains purpose that predates us. Purpose that's been embedded in the structure of space and time, encoded in the arrangement of stars, built into the fabric of reality. We're not accidents, we're inheritors. We're part of a story that's been unfolding for billions of years, a story written by minds that thought on timescales we can barely comprehend. This doesn't mean the universe has a predetermined destiny or that our lives are scripted, but it does mean that we're part of something larger than ourselves, something that connects us to the deepest past and the farthest future. Our actions matter, not just to us and our immediate descendants, but to the long-term fate of the galaxy itself. It also changes how we think about consciousness. If the builders existed, if they built galaxies and maintained them for billions of years, then consciousness isn't a brief anomaly in an otherwise dead universe. It's fundamental, it's persistent, it's capable of surviving for timescales that make biological evolution look like a brief flickering. What form did their consciousness take? Were they biological, like us? Did they upload themselves into computers, becoming digital beings? Did they transcend the physical entirely, becoming something we'd recognize as pure thought or pure energy? We don't know. But the fact that they existed at all, that they achieved what they achieved, proves that consciousness can persist and grow and accomplish things that seem impossible, and that means we can too. Our consciousness, fragile as it seems, locked in these bodies that last only decades, might be just the beginning. We might be larvae, early forms of something that will eventually span the galaxy and last for billions of years. Death might not be an ending, but a transformation, a transition from one form of consciousness to another. These are ancient questions, of course. Every religion and philosophy has grappled with them. But the idea of artificial galaxies gives them a new context, grounds them in physics and astronomy rather than pure speculation. It suggests that transcendence isn't just a spiritual concept, but a technological possibility, that the afterlife might not be a separate realm, but a continuation of consciousness in forms we haven't yet developed. Let's get specific. Let's talk about how you would actually modify a star. Stars are not solid objects. They're not machines with parts you can replace. They're massive balls of plasma held together by gravity, with nuclear fusion happening in their cores. The outer layers convect and radiate, moving energy from the core to the surface. Magnetic fields twist through the plasma, creating sunspots and solar flares. It's chaos, but it's predictable chaos. We can model it. We understand the physics. And if we understand it, we can manipulate it. The simplest intervention would be mass adjustment. A star's lifetime is determined by its mass. Massive stars burn hot and fast, exhausting their fuel in just millions of years before exploding as supernovae. Small stars burn cool and slow, potentially lasting for trillions of years. Our sun is somewhere in the middle. It will last about 10 billion years total, and it's currently about halfway through its life. If you wanted to extend a star's life, you'd need to remove mass. This sounds impossible, but it's actually straightforward in principle. You could use massive orbital mirrors or magnetic fields to blow off the star's outer layers, reducing its total mass without disrupting the fusion in the core. Less mass means lower pressure in the core, which means slower fusion, which means the star lasts longer. Or you could do the opposite. You could add mass, making the star burn brighter and hotter. This would be useful if you needed more energy in the short term and didn't care about longevity. You'd harvest gas from nearby nebulae or dismantle planets and feed them into the star, gradually increasing its output. But there's a more sophisticated approach, core manipulation. The fusion rate in a star's core depends on temperature and density, which are both determined by the star's mass and composition. If you could inject heavier elements into the core, carbon, oxygen, iron, you could change the fusion dynamics without adding or removing bulk mass. The star would burn differently, produce different wavelengths of light, last longer or shorter depending on what you added. How would you inject material into a star's core? The core is buried under hundreds of thousands of kilometers of dense plasma. You can't just drill down, but you could use gravitational focusing. Drop a dense object, maybe a small black hole or a nugget of exotic matter, into the star. As it falls toward the core, it would pull material with it, creating a channel through the plasma. You could use that channel to inject whatever elements you wanted, then remove the dense object before it disrupted the core too much. This is speculative, yes, we've never done anything like this, but the physics allows it. There's no fundamental law that prevents stellar engineering. It's just very, very difficult with our current technology. And then there's the question of stellar positioning. Stars orbit the galactic center, but their orbits can be altered. If you wanted to arrange stars in a specific pattern, say to optimize energy, collection, or create a habitable zone free from supernova risks, you'd need to move them. The energy required to move a star is enormous, but again, you don't need to overpower gravity, you just need to nudge. A small gravitational assist here, a slight course correction there, applied over millions of years, and the star ends up where you want it. One proposed method is called a Shkadov thruster. You build a massive mirror, kilometres across, made of ultra-thin reflective material, and position it on one side of the star's light pushes against the mirror, and by Newton's third law, the mirror pushes back against the star. It's like a solar sail, but instead of pushing a spacecraft, it's pushing an entire star. The acceleration is tiny, fractions of a millimetre per second per year, but over geological timescales it adds up. Given enough time, you could move a star across the galaxy. A more advanced version is the Kaplan thruster, which uses the star's own material as propellant. You build a massive fusion reactor that scoops up hydrogen from the star's outer layers, fuses it into heavier elements, and ejects it at high speed. The exhaust creates thrust, pushing the star in the desired direction. This is more efficient than a mirror because you're not relying on radiation pressure alone. You're using the star as a fuel source for its own engine. Now imagine doing this to billions of stars. Imagine a civilization that's been running stellar engines for hundreds of millions of years, slowly rearranging the galaxy into an optimal configuration. From our perspective, looking at the galaxy through our telescopes, we'd see what appears to be a natural distribution of stars. But in reality, every star would be exactly where it was meant to be, positioned by engineers who thought on timescales longer than our entire evolutionary history. Would we be able to detect this? Maybe. If we could measure stellar velocities with extreme precision, we might notice that some stars are moving in ways that don't quite match gravitational predictions. They're not where they should be, or they're moving slightly faster or slower than expected. Individually, each anomaly would be small, explainable as measurement error or natural variation. But if we found thousands of such anomalies, all pointing in the same direction, all suggesting deliberate movement, that would be harder to explain away. This is the kind of signature we should be looking for. Not obvious megastructures, not radio signals, but subtle deviations from natural patterns. Engineering at this scale would be nearly invisible, but not quite. There would always be traces, anomalies, hints that something was guiding the process. Here's something we haven't addressed yet. If galaxies are artificial, what about life? We know life exists, we're proof of that. Earth is teeming with biological organisms, from bacteria to blue whales, from viruses to humans. Life has been present on this planet for at least 3.5 billion years, and possibly longer. It's diverse, resilient, and fundamentally dependent on chemistry, on the right elements in the right concentrations at the right temperatures. And all of that depends on stars. The heavy elements that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, were created in stars. Hydrogen and helium formed in the Big Bang, but everything else was forged in stellar cores or supernova explosions. We are literally made of stardust, the processed remnants of stars that died before our sun was born. If a Type 3 civilization is engineering galaxies, they're not just arranging stars for energy collection, they're managing the chemical evolution of the entire galaxy. Every supernova distributes heavy elements into the interstellar medium, enriching the gas clouds that will eventually collapse to form new stars and planets. Every generation of stars increases the metallicity of the galaxy, making it more capable of producing rocky planets and, potentially, life. This is called nucleosynthesis, and it's a well-understood process. We know how elements are created, how they're distributed, how they contribute to the formation of planets. What we don't know is whether this process could be managed. Could a sufficiently advanced civilization control which stars go supernova, and when? Could they harvest the ejecta from those explosions and distribute it in specific patterns, seeding certain regions of the galaxy with the elements needed for life? Could they adjust the initial metallicity of star-forming regions to optimize the chances of habitable planet formation? If the answer is yes, and the physics suggests it might be, then the existence of life in a galaxy isn't random. It's intentional. The builders wouldn't just be creating energy infrastructure, they'd be creating conditions for life to emerge and evolve. But why would they do this? Maybe for the same reason we build gardens. Because life is beautiful, interesting, worth preserving. A galaxy filled only with stars and machines would be functional, but sterile. A galaxy that also contains biological life, ecosystems, evolutionary processes, the emergence of intelligence, would be far richer, far more complex. It would be a work of art as much as an engineering project. Or maybe life is functional. Maybe biological organisms serve a purpose in the galactic ecosystem that we don't understand yet. Maybe they're computational substrates, processing information in ways that digital systems can't replicate. Maybe consciousness itself is valuable, a resource that can only emerge from biological or biological adjacent systems. Maybe the builders seed galaxies with life because consciousness is the whole point. This would explain something that's always been puzzling: the timing of human emergence. The universe is 13.8 billion years old. The Earth is 4.5 billion years old. Complex life only emerged in the last billion years or so, and humans appeared in just the last few 100,000 years. We're incredibly recent, cosmically speaking. If the galaxy is billions of years old, why didn't intelligence emerge sooner? One possible answer: because the conditions weren't right yet. Because the builders needed time to prepare the galaxy, to adjust the chemical composition, to arrange the stars in stable configurations, to ensure that when life did emerge, it would have a chance to survive and thrive. We're not early, we're right on schedule. Look at our solar system. It's remarkably stable. The planets orbit in nearly circular paths, all in roughly the same plane. The inner rocky planets are small and warm, the outer gas giants are large and cold. Jupiter acts as a gravitational shield, deflecting many of the comets and asteroids that might otherwise bombard Earth. The Moon stabilizes Earth's axial tilt, preventing extreme climate swings. It's all very convenient. Too convenient? Maybe. The standard explanation is that we observe this stability because we couldn't exist otherwise, the anthropic principle again. But what if our solar system isn't typical? What if it was designed, or at least arranged, to be a stable cradle for life? We've discovered thousands of exoplanets in the last few decades, and many of them are in systems very different from ours. Hot Jupiters orbiting close to their stars, planets with wildly eccentric orbits, systems with no apparent structure or stability. Maybe those are the natural systems, and ours is the engineered one. Testing this would be difficult. We'd need to find statistical patterns in planetary systems across the galaxy, looking for evidence that some systems are more stable, more optimized, more designed than others. We'd need to understand which features are necessary for stability and which are optional, and we'd need to explain why some systems would be engineered and others left natural. But if we found such patterns, it would be powerful evidence. It would suggest that the galaxy isn't just a collection of stars, but a managed ecosystem where life is deliberately cultivated. Let's get concrete. Let's look at specific galaxies that make astronomers uncomfortable, that have features we struggle to explain. Start with Hoag's object, discovered in 1950 by astronomer Art Hoag. It's a ring galaxy, a nearly perfect circle of bright stars surrounding a spherical core, with a gap of mostly empty space between them. Ring galaxies are rare, and we think they form when a smaller galaxy passes through the centre of a larger one, creating a gravitational ripple that propagates outward like a wave in water. The collision disturbs the orbits of stars and they settle into this ring structure. That's the theory. But Hoag's object is almost too perfect. The ring is nearly circular, evenly distributed with no obvious disturbances. If it formed from a collision, where's the evidence of the smaller galaxy? It should still be there, or we should see its remnants. But we don't. The core is smooth and featureless, and the ring looks like it was drawn with a compass. Maybe it's just a very old collision, and the evidence has faded. Maybe the smaller galaxy was completely disrupted and absorbed. Maybe our models are missing something, or maybe it's artificial. Maybe the ring is a deliberate structure, a massive Niven ring scaled up to galactic proportions, and the gap between the core and the ring is functional space, designed for purposes we can't fathom. Then there's the Cartwheel Galaxy, another ring galaxy with even more dramatic structure. It has a bright inner ring, a dim intermediate zone, and a bright outer ring, all perfectly concentric. It looks like a target, like someone drew circles around a central point. We think it formed from a high-speed collision about 200 million years ago, but again, the symmetry is striking. The rings are too even, too perfect. Consider also NGC 1277, a galaxy in the Perseus constellation that's sometimes called a relic galaxy. It's massive, about twice the size of the Milky Way, but it contains stars that are all roughly the same age, around 12 billion years old. It seems to have stopped forming new stars billions of years ago, which is unusual. Most galaxies continue forming stars over time, feeding on gas from their surroundings. But NGC 1277 is quiescent, dormant, as if it completed some process and then shut down. What if it's not dormant? What if it's finished? What if it's a completed megastructure that no longer needs to grow because it's achieved its design specifications? And then there's the case of ultra-diffuse galaxies, or UDGs. These are galaxies that are roughly the size of the Milky Way but contain far fewer stars, sometimes 100 times fewer. They're so faint that they're nearly invisible, and we've only discovered them in the last couple of decades as our instruments have improved. We don't understand how they form. They shouldn't be stable. Their gravity is too weak to hold them together. But they exist, dozens of them, scattered through galaxy clusters. What if they're not natural? What if they're artificial structures that only look like galaxies? What if the visible stars are just a small component of a much larger infrastructure that we can't see, and the stars themselves are there for decorative or functional reasons we don't understand? There's also the mystery of the Virgo supercluster and the Great Attractor. We know that our galaxy is moving through space, pulled by the gravity of nearby structures. But when we measure the velocities of galaxies in our local region, we find that they're all moving toward a point beyond the Virgo supercluster, towards something called the Great Attractor. We can't see it directly, it's hidden behind the plane of the Milky Way, but we can infer its presence from the motion of surrounding galaxies. The mass of the Great Attractor, based on its gravitational effects, should be enormous, tens of thousands of galaxies worth. But when we look in that direction with radio and infrared telescopes that can penetrate the dust of the Milky Way, we don't find enough visible mass to account for the attraction. Something is pulling us, but we can't see what it is. Dark matter is the standard explanation. There's a massive concentration of dark matter in that region, and it's pulling on the surrounding galaxies. But what if it's not dark matter? What if it's a structure, a megastructure, something so large that it warps the gravitational field of an entire supercluster? What if the Great Attractor is the galactic equivalent of a city, a hub where multiple artificial galaxies have been connected into a single unified system? We can't prove any of this. For every anomaly, there are natural explanations that fit the data reasonably well. But the accumulation of anomalies is suggestive. One strange galaxy is a curiosity, 10 is a puzzle, 100 starts to look like a pattern. Here's a method of detection we haven't discussed yet: gravitational waves. In 2015, humanity detected gravitational waves for the first time, ripples in space-time caused by the collision of two black holes over 1 billion light-years away. It was a triumph of physics and engineering, confirming a prediction Einstein made a century earlier. Since then, we've detected dozens more events: black hole mergers, neutron-star collisions, and we're constantly improving our sensitivity. Gravitational waves are unique because they pass through everything. Unlike light, which can be blocked by dust or absorbed by gas, gravitational waves travel unimpeded across the universe. If you create a massive enough disturbance in space-time, anyone with the right instruments can detect it, regardless of what's in the way. And moving stars creates gravitational waves. They're tiny, far smaller than the waves from black hole collisions. But if you're moving millions of stars simultaneously, adjusting their orbits, steering them into new configurations, the cumulative effect might be detectable. It would be a very specific signature. Not a sudden burst like a collision, but a continuous, low-frequency hum, the gravitational equivalent of a background noise. Current gravitational wave detectors like LIGO and Virgo aren't sensitive enough to detect this. They're designed for high-frequency events, not the slow, steady signals that stellar engineering would produce. But future detectors might be. The Laser Interferometer Space Antenna, or LISA, is a planned space-based gravitational wave observatory that will be sensitive to much lower frequencies. It's designed to detect the gravitational waves from supermassive black hole mergers and other massive slow-moving sources. If LISA, or a similar instrument, detected a persistent gravitational wave signal coming from a galaxy, and that signal had the characteristics of multiple massive objects moving in coordinated patterns, it would be extraordinary evidence. It wouldn't be conclusive on its own. Natural processes can also produce gravitational waves, but combined with other anomalies it would be hard to explain. Think about what coordinated stellar motion would look like gravitationally. It wouldn't be random. It It would have structure, periodicity, patterns. If billions of stars were being moved according to a plan, their gravitational signatures would interfere and combine in specific ways, creating harmonics, beats, rhythms. It would be like listening to an orchestra and hearing not random noise but a symphony. Could we distinguish between natural gravitational waves and artificial ones? Maybe. Natural sources tend to be chaotic or follow simple patterns determined by orbital mechanics. Artificial sources might show optimization, efficiency, coordination that's too precise to be accidental. We'd need sophisticated analysis, machine learning algorithms trained to recognize the signatures of engineering, but it's possible. And if we found such a signature, we'd have to confront the possibility that we're detecting active galactic engineering happening right now, not billions of years ago. We'd be hearing the machinery at work. Let's talk about something practical: maintenance. If galaxies are artificial, they can't be static. They need to be maintained, adjusted, repaired. Stars burn out, orbits decay. Unexpected events, like rogue planets or wandering black holes, can disrupt carefully arranged systems. Over millions of years, entropy takes its toll. Any structure, no matter how well designed, will eventually break down without active maintenance. So what would galactic maintenance look like? First, there's stellar replacement. Stars have finite lifetimes. When a star reaches the end of its life, it either collapses into a white dwarf, neutron star, or black hole, or it explodes as a supernova. In either case, it stops being a useful energy source. A civilization managing a galaxy would need to replace dead or dying stars with new ones. The obvious source of new stars is the interstellar medium, the gas and dust between the stars. Normally this material slowly coalesces under gravity, forming new stars over millions of years. But if you're managing the process, you could accelerate it. You could compress gas clouds artificially, triggering star formation on demand. You could control the mass of the forming stars, ensuring you get the right kind: long-lived, stable, energy efficient. This would show up in observations as unusual star formation patterns, regions where stars are forming faster than expected, or where the distribution of stellar masses is different from the standard models. We do observe variations in star formation rates across different galaxies and different regions within galaxies, but we usually attribute them to differences in gas density, metallicity, or other natural factors. What if some of these variations are artificial? Second, there's orbital correction. Even with perfect initial placement, stellar orbits will drift over time due to gravitational interactions. A close encounter with another star, a passing gas cloud, the slight asymmetry in the galactic gravitational field, all of these can perturb orbits. Left uncorrected, these small deviations accumulate, and eventually the carefully designed structure starts to blur. Correcting orbits requires continuous monitoring and adjustment. You'd need a network of sensors tracking every star, calculating its trajectory, predicting deviations, and activating correction mechanisms when necessary. For a galaxy with billions of stars, this would be an enormous computational task, but not impossible for a sufficiently advanced civilization. What would the correction mechanisms be? Probably the same tools used for initial positioning: Shkadov thrusters, gravity assists, mass adjustments, but applied continuously in small doses, keeping the galaxy tuned like a musical instrument. Third, there's disaster response. Space is dangerous. Supernovae explode, gamma-ray bursts sweep across the galaxy, black holes wander through star systems. An artificial galaxy would need defenses against these threats. You might be able to predict when a star will go supernova and evacuate the surrounding region, or use magnetic fields to deflect the ejector. You might build shields or barriers around critical infrastructure, or maintain buffer zones free of volatile stars. And then there's collision management. Galaxies collide. It's a natural part of cosmic evolution. Our own Milky Way is on a collision course with the Andromeda Galaxy, and they'll merge in about 4.5 billion years. The collision will be spectacular, a slow-motion dance lasting hundreds of millions of years as the two galaxies interpenetrate, their stars passing through each other like ghosts, their gravitational fields pulling them into new configurations. If both galaxies are artificial, what happens to the infrastructure? Does it survive the collision, or is it destroyed? Do the civilizations that built them coordinate the merger, ensuring that critical systems are preserved? Or is a galaxy collision the cosmic equivalent of a demolition, the end of one era and the beginning of another? We have no idea. But if we could observe a collision between two galaxies and detect evidence of controlled behaviour, systems shutting down in an orderly fashion, stars being moved out of harm's way, energy being redistributed, it would be extraordinary evidence of intelligence at work. Let's think about resources for a moment. Let's think about the economics of building and maintaining a galaxy. A Type 3 civilization has access to essentially infinite energy. Every star is a power source. Collectively, they produce more energy than any conceivable civilization could use. So energy isn't the limiting factor. Materials aren't a problem either. Stars contain enormous amounts of hydrogen and helium, and supernovae produce heavy elements. If you need more of a specific element, you can create it through nuclear processes. With enough energy, you can transmute anything into anything else. Matter is just energy in a different form, and you have all the energy you could ever need. So what is the limiting factor? What constrains a Type 3 civilization? Time, maybe. Even with perfect technology, some processes just take time. Moving a star from one side of the galaxy to the other, even with a Shkadov thruster, takes millions of years. Building a Dyson swarm around 1 billion stars takes time, even if you can manufacture the components quickly. Coordinating actions across light years of space introduces communication delays that can't be overcome. Signals travel at the speed of light. Period. But time might not feel like a constraint if you're a civilization that thinks on timescales of millions of years. If your planning horizon extends thousands of generations into the future, then a project that takes 10 million years is just a long-term investment. You start it knowing you won't see it completed, that your descendants' descendants will be the ones to benefit. But you start it anyway, because that's what civilization does. It builds for the future. Information might be a constraint. Managing a galaxy requires knowing what's happening everywhere, all the time. You need sensors, communication networks, data processing, decision-making systems. The amount of information flowing through a galactic-scale civilization would be staggering. Far more than any biological brain could process, even any conceivable computer. Unless you distribute the computation, unless you embed intelligence into the structure of the galaxy itself, making every star, every planet, every cubic light-year of space part of a vast computational network, the galaxy becomes a computer, and the civilization becomes software running on that hardware. This is the concept of a Matryoshka brain, proposed by Robert Bradbury, a megastructure built around a star, designed to use all of the star's energy for computation. A galaxy-scale version would be a network of billions of Matryoshka brains, all linked together, forming a distributed intelligence of incomprehensible scale. If this is what a Type 3 civilization looks like, if they've transcended biological form and become pure information, running on hardware made of stars, then they wouldn't think the way we do. They wouldn't have bodies, emotions, individual identities in any sense we'd recognise. They'd be something else entirely. Something that might look like a galaxy but thinks like a god. And we, looking at such a structure, would see stars and gas and the normal machinery of astronomy. We wouldn't recognise the intelligence, because it's operating on a level so far beyond us that we don't have the concepts to understand it. Here's something we keep coming back to, but haven't fully explored: aesthetics. If you're a Type 3 civilization with effectively unlimited resources and millions of years to work with, you don't just build for function, you build for beauty, you make art. And what better canvas than a galaxy? Think about the spiral arms. They're not necessary for galactic function. A galaxy could just be a spherical distribution of stars all orbiting the centre in random directions. That would work fine for energy collection and resource management, but it would be boring. It would lack elegance. Spiral arms are beautiful. They're dynamic, flowing, organic. They create patterns of light and shadow when viewed from outside. They suggest motion, growth, evolution. If you were designing a galaxy and you cared about aesthetics, you'd probably include spiral arms. The same goes for symmetry. Perfect symmetry is rare in nature. It usually indicates either artificial design or very specific physical constraints. When we see galaxies that are unusually symmetrical with evenly spaced features and balanced proportions, maybe we're seeing the aesthetic preferences of their builders. Maybe they valued symmetry just as many human cultures do. Maybe they built their galaxies to be beautiful, not just functional. And colour. Stars come in different colours depending on their temperature. Red for cool stars, orange and yellow for medium stars, blue and white for hot stars. The colour of a galaxy depends on which types of stars dominate. Old galaxies tend to be red because they contain mostly old, cool stars. Young galaxies are bluer because they're actively forming hot young stars. If you're building a galaxy, you can choose its colour palette. You can decide what proportion of red, orange, yellow and blue stars to include, creating a specific visual appearance. You could even arrange stars in patterns, creating pictures or symbols visible to anyone looking at the galaxy from the right angle. This sounds far-fetched, but consider, humans have been making art for tens of thousands of years. It's one of the defining features of our species. We paint, sculpt, compose music, write poetry. We create beauty because we can, because it gives our lives meaning, because the alternative, a world without art, is unthinkable. Why would a civilization that's billions of years old be any different? If anything, they'd have even more reason to create art. They've solved all the practical problems: survival, resources, energy, longevity. What's left? What do you do when you have infinite power and infinite time? You create. You build wonders. You make things that are beautiful, not because they serve a function, but because beauty itself is the function. A galaxy could be the ultimate artwork, a sculpture on the largest possible scale, designed to last for billions of years, to be admired by anyone with eyes to see it. And if that's true, then every galaxy we observe might be someone's masterpiece. Every spiral arm, every elliptical cloud, every irregular tangle of stars might be a deliberate composition, as carefully crafted as any painting or symphony. We look at these structures and see physics, we see gravity, gas dynamics, stellar evolution. But what if we're missing the art? What if we're like people who analyse a painting by measuring the chemical composition of the pigments, completely oblivious to the image the artist was trying to create? Let's return to the Fermi paradox one more time, but from a different angle. Let's ask, not, where are they, but what would success look like? Imagine humanity survives. We make it through the next few centuries without destroying ourselves. We solve climate change, avoid nuclear war, develop sustainable technology. We spread to other planets, then other stars. We keep growing, keep learning, keep building. Eventually, maybe in 10,000 years, maybe in a million, we reach Type 3 status. We've reshaped the galaxy. We've built Dyson swarms around millions of stars. We've extended our lifespans to thousands of years, or uploaded our consciousness into digital substrates that can last indefinitely. We've created a civilization that spans the galaxy and thinks in terms of billions of years. What would we want? Stability, probably. Safety. A galaxy where existential risks have been eliminated, where nothing can threaten the civilization we've built. We'd want to preserve what we've created to ensure it lasts as long as possible, and we'd want... what? More. Growth. Expansion. Maybe not. Maybe at some point you have enough. Enough energy, enough space, enough time. You've achieved everything you set out to achieve. The galaxy is yours, it's safe, it's optimized. What's left? You could keep expanding, spreading to other galaxies. But that takes time. Hundreds of millions of years to reach even the nearest galaxies, and communication delays make it nearly impossible to maintain a unified civilization across intergalactic distances. You'd essentially be creating daughter civilizations that would diverge and become independent. Maybe that's fine. Maybe that's the natural progression. Or you could turn inward. You could focus on refinement rather than expansion. You could perfect your technology, explore every possible form of art and philosophy and science. You could create virtual realities of infinite complexity, simulated universes where you can explore scenarios that don't exist in base reality. You could become a quiet civilization, one that's achieved success and now wants simply to enjoy it. And that civilization would be invisible. It wouldn't broadcast its presence. It wouldn't build obvious monuments or send out greeting cards to younger species. It would just exist, humming along, managing its galaxy, creating and exploring and living, completely indifferent to the rest of the universe. This is what success looks like. It looks like silence. We expect aliens to be loud because we're loud. We're young, ambitious, desperate to make contact, to learn, to grow. We send out radio signals and golden records and messages to the stars because we want to be noticed, want to be part of something larger. But maybe that's a phase. Maybe it's what young civilizations do before they mature and realise that broadcasting your presence is either dangerous or pointless or both. Maybe the successful civilizations, the ones that have survived for billions of years, have all learned to be quiet, to build their megastructures in ways that look natural, to enjoy their success without making a fuss about it. If that's true, then the Fermi paradox isn't a paradox. It's exactly what we should expect. The universe is full of successful civilizations, but success means silence. It means invisibility. It means that when we look at the stars, we see only what appears to be nature, because the civilizations have become indistinguishable from it. And someday, if we're very lucky, if we survive and grow and reach for the stars, we'll join them. We'll become one of the quiet ones, the successful ones, the civilizations that have learned that the greatest achievement isn't to announce your existence, but to perfect it. We'll build our own galaxy, or reshape the one we're in, and we'll make it beautiful and stable and safe, and we'll live in it, quietly, for billions of years, creating and exploring and enjoying the universe we've made. And if younger civilizations look at our galaxy and wonder if anyone's home, we'll smile and say nothing. We'll let them figure it out on their own, just like we had to. Because that's the test. That's how you prove you're ready. Not by shouting into the void, but by learning to see what's already there. So where does this leave us? After all these words, all this speculation, all these questions, we still don't know if galaxies are artificial. We might never know for certain. The evidence is ambiguous. The anomalies can be explained naturally. The universe keeps its secrets well. But we've learned something valuable, that the question itself changes how we see the cosmos. That once you start thinking about galaxies as potential megastructures, you notice things you wouldn't have noticed otherwise. Patterns that seem too regular, symmetries that seem too perfect, efficiencies that seem too optimized. Maybe it's all confirmation bias. Maybe we're seeing design where there's only chance. Maybe the universe really is just physics and chemistry, with no intelligence behind it except the brief flickers of consciousness like us, struggling to understand our place in the vastness. Or maybe not. Maybe the galaxies we see glittering in the darkness are monuments, machines, artworks, evidence of minds so vast, so ancient, so different from us that we can barely conceive of their existence. And maybe, just maybe, we're starting to understand. We're asking the right questions, developing the right tools, learning to see the universe as it actually is rather than as we assumed it must be. The search continues, the telescopes get better, the data accumulates, and somewhere in the patterns of light and gravity that cross the universe, there might be a message, a signature, a sign that we're not alone, that we've never been alone, that the cosmos is full of wonders we've only begun to perceive. Keep looking, keep wondering, keep asking what if. Because the answer, when it comes, will change everything. And until then, the galaxies wheel in the darkness, silent and eternal, keeping their secrets, waiting for us to grow wise enough to understand them. The universe is patient. It's been waiting for billions of years. It can wait a little longer.